Dear students, welcome to another day's lecture in Elements of Machine Design. Yesterday we started a new topic um and we discussed about the power screws, the introduction, and the torque required to raising the load and lowering the load. Today let us see about the efficiency of the screw. See, the efficiency uh, is the ratio of ideal effort. Ideal effort means the what it should be, the right effort. When will you be able to lift the load without any friction? You will be able to lift. That means ideal effort means when there is no friction. So it is the ratio of ideal effort to actual effort. That means actually what we are putting effort. Okay, the ratio of these two is called as the efficiency of the screw. Okay, this is the definition. Okay, now we have seen that the effort required to raise the load, we are only talking about effort, not the torque. So the d by 2 term will not be there in the torque. Okay, P is equal to W, that is the weight that we are lifting. P is the effort that we are exerting, into tan of alpha plus phi, or phi plus alpha, you can say. Okay, see, in the ideal case, the ideal effort where there is no friction, that means phi is 0. If friction, this phi is what? Friction angle. Alpha is helix angle. If this is 0, then what will happen? This becomes 0 means only tan alpha will be left. Then that means what? The ideal effort uh, PO is equal to W tan alpha. This is what the effort is required to raise the load when there is no friction. So, but when it is friction is there, this is the formula. These are the two formulae, without friction and with friction. So now the efficiency is the ratio of these two, the ideal effort upon the actual effort, into 100. This is the percentage efficiency, that is percentage eta is PO upon P into 100. So now what you get here, this one, see, now W and W will be cut. Okay, what is the efficiency formula then? Efficiency eta is equal to tan alpha upon tan of alpha plus phi into 100. That will give you the percentage efficiency of the screw. Okay, and let us discuss now about the self-locking and overhauling of screw. Yesterday also I touched a little, because I gave some questions about self-locking and overhauling in your quiz. I touched a little. Okay, anyway, now let us see, including the mathematics behind it. Self-locking and overhauling of the screw. These are the two terms which are associated with the lowering of the load. You see, this is the load effort that is required when you have to lower. You see, lowering means what? You see, when the load is coming down. Okay, this is tan of phi minus alpha. Okay, and you see, if it is raising, it will be plus here. If it is lowering, it is minus. Okay, we also know that the torque required to lower the load is, this is the effort, and the effort multiplied by d by 2 will be the torque. The same thing, this is P into d by 2. Okay, this is the torque. Okay, so in these equations, if the friction angle is less than or equal to less than if the friction angle is less than the helix angle, then the effort and torque become negative. You see, suppose, you see, this phi is there, this alpha is there. As long as phi is more, this whole term will be positive. If alpha becomes more, how alpha will become more? The slope, no, you are increasing. You see, if the ramp, no, you see ramp, the slope, no, you see, when it is less slope, you will not find it difficult to climb. Not so much. But if you have a steep, that means very sharp rise is there, then you will find it difficult. You see, you find it difficult to climb mountains. Mountains, the slope is, very steep. Therefore, you see, like that, in our case of the threads also, if the helix angle is very steep, that means this angle alpha is more, okay, than this. Then what becomes is, this entire term becomes negative. Negative torque is required to lowering the load. That means what? You see, the torque becomes negative. Therefore, the load works positively and starts moving downward without any effort. And the torque, and without any effort and torque, this condition of the screw is called as overhauling of screw. This is the term overhauling. Okay, but however, in above equations, if the friction angle is more greater than the helix angle, that is phi is more than alpha, then effort and torque become positive. Positive means you have to definitely apply effort. You have to definitely apply torque. Now, negative means you need not. You see, like that. So therefore, load works positively and effort is required to lower the load. This condition of the screw is called as self-locking of the screw. Now you understand these two terms. Overhauling means without our applying any effort, the load by itself is coming down. Okay. Self-locking means, it will not come by itself. You, even for lowering the load, you have to apply effort. Okay, such a case is called as self-locking of the screw. Okay, so uh, this is the efficiency formula. Efficiency eta is equal to tan alpha upon tan alpha plus phi. Okay, this is the efficiency formula. Okay, now sometimes question is asked in the exams. You prove that for a self-locking screw, this efficiency is always less than 50%. This efficiency is always less than 50%. You prove, that is the question. Okay, now this is the answer. From here to here, what is there? This is the answer. Okay, this may be asked for some 4 marks or something, or it could be for less also, because now you are giving paper only for 70 marks. It could be 2 marks, 3 marks also. But anyway, this is not very difficult. You see here, eta is equal to tan alpha upon tan alpha plus phi. This is the efficiency formula. Now, what is the condition for self-locking screw? Self-locking screw, phi for friction angle should be either equal or greater than alpha. Friction angle should be more than the helix angle. Okay, now in the limiting case, let us assume that phi is equal to alpha is equal to phi. Okay, so therefore let us substitute alpha with phi. Okay, now what happens? The see, this becomes tan phi. This is tan phi plus phi, so it becomes tan phi upon tan 2 phi. Okay, tan 2 phi. This tan 2 phi. If you mathematically in trigonometry you may have learned, tan 2 phi is equal to um, tan 2 phi is equal to 2 tan phi upon 1 minus tan square phi. That is the thing. Okay, this is how it is. So now this tan phi gets cut, and what remains is only 1 minus tan phi square by 2. This will remain. Now if you take this term separately, this becomes half, and this becomes tan square phi by 2. Okay, and this is Now phi eta is equal to 0.5 minus tan square phi by 2. And now you see this is a negative term. You see, how much ever this value will be, if this value is 0, it will be 0.5. If this is zero point 0.1, it will become only 0.4. Are you seeing? Any value of phi here will make it more less than 0.5 only, not more than 0.5. Half. 0.5 means half. Okay. So that means what? The efficiency can never be more than half. Half means 50%. Okay. So from the above equation, it is observed that for the self-locking locking screw, efficiency will be less than 50%. See here, the self-locking condition we have applied. What is the self-locking condition? For self-locking condition of the screw, the phi should be greater than or equal to alpha, and we have substituted this value. Alpha is equal to 5 we have substituted, and then we have derived, and we have found out that the efficiency cannot be more than 50% for a self-locking screw. If it is more than 50%, then it should be mm, overhauling screw or something. Okay. Now let us see a screw jack. This screw jack, this is often this is the thing we are expected to design. Okay, screw jack. Now how is the screw jack? See, screw jack. This is a cut section. It is cut in the middle. That means, okay. Now you see here the thing that I'm showing here. This one is the body. Okay, this is a body. Here it is written body. This is the base of the body. It is made wider so that it may have more stability. Okay, and in this body here on the top, no, it is inserted. What is inserted? Nut is inserted. This is called nut. Nut is inserted. Okay, this nut has threads inside. Nut has internal threads. Okay, and you see this screw is inserted in the nut. The screw has outside threads. This is the screwed spindle. A long long screwed spindle is there. Okay. On the bottom side, there is some locking arrangement, like a washer is there, nut is there provided, so that no, when you are turning the screw, it should not come out of the nut. Okay, when it comes and touches here, it should stop. Okay, that's why this some locking arrangement is there. Okay, on the top, what is there? On the top of the screw, you have a head. So from the head bottom to down, you have the screw. So on the head, no, what you have is you will be having holes like this. You see, this hole is for inserting this rod. This is, you can call it as Tommy bar, you can call it as handle, or you can call it rod, anything. Okay, this is the rod we insert into the hole. It may be having a number of holes. Now you see, once you remove it, there under the truck or something, you'll not have much place. So these holes may be either at 60-degree angle or 90-degree angle also. If 60-degree angle means at least how many should be there? 3 holes should be there. If it is 90-degree angle, 2 holes should be there. Okay, like that. So above this head, there is a pin here, some projecting part here. This projecting part, okay, that is called pin, and on that also you can put a washer and screw, because on this is put one cup. This is a cup. Okay, this cup is there, and this cup should not fall off. That's why you can put a washer and a screw and tighten. That means this should have hole. Okay, that this should have a tapped hole for the screw to be tightened. Okay, and then this is the cup. Okay, this cup, no, on the cup only we will be putting the weight means, suppose you are lifting a truck, so the truck weight will be there. Okay, now what is the use of this cup? This cup, no, see, suppose you are rotating this, and if this cup is not there, and if the truck is directly sitting on this head, you see the entire truck also should rotate if this is head is rotating. But the truck should not rotate. Okay, therefore, you see, it is put on the cup here. So when this head is rotating, this cup will be stationary. So there will be here, you see in the contact here, there will be friction here. Okay, and this is how our screw jack looks. There are many models of screw jacks. You may find different things, but for our design what we do is this. And here you see there is one locking, for our locking arrangement. You see here, this nut is there, no, this nut should not rotate in the body. So to prevent the rotation, no, they put some grub screw or some other locking arrangement they'll put. Okay, and this nut also has a little flange like this, or you can say collar. Why collar? Because otherwise the nut will go inside also, inside and fall off. It should stop somewhere. So this nut will be fitting, and this, see, there are no threads on this side of the nut. There are threads here, but this side of the nut there are no threads. So how is it put? There may be, maybe, uh, some interference fit or some clearance fit may be there. But anyway, to ensure that it will not rotate, we are using this screw. This a small grub screw we may use. Okay, this is how a screw jack is. Now let us see this screw jack. You see, DC is the core diameter. DC means, this screw has inside. What are we designing? We are more interested in designing the threads here. Not the other part so much. Okay, DC is the core diameter, DO is the nominal diameter. DC core diameter, DO is the nominal diameter, and DM is the mean diameter. Okay, and capital D1 is the inner diameter of the nut. Capital D1, this one is the inner diameter. Inner diameter means, actually this is the inner diameter will be the core diameter only. This one is D1, and this outside diameter of the nut collar is D2, and D3 is the diameter of the head. This one is D3. This head, this is D3, and D4 is the diameter of the pin collar. This one is D4, and D5 is the diameter of the body top. Uh, D5 body, this is the body. This body stop means from here to here, D5. Yeah, this is shown here, D5. And D6 is the inside diameter of the bottom, that is this one, inside diameter D6. And D7 is the outside diameter of the bottom, that is this one. You see, these are all in proportions only. We need not be bothering about designing all this. Okay, then T is the width or thickness of the screw thread. Width or thickness of this screw thread, that is the threads inside, what is there. And T1 is the thickness of the nut head. You see, this is the T1, and T2 is the thickness of the base. This one is T2 here, and T3 is the thickness of the body. This is the thickness of the, what is that, thickness of the body, T3. Oh, this one is the thickness. You see, this is T3, and H is the height of the nut. This is the height of the nut. Mm. Nut nut is this one. So this is that head height h, and then this is not h. They have put h here also. This only is h. Okay, and the L is the length of the lever, and this is the lever, or Tommy bar. Tommy bar's length is L, and the height of the head is 2 times of d. This is height of the head actually. This is not h. This is 2 times of d. This h you can remove. Otherwise, you can say capital H1. Then the height of the body is maximum lift plus max height of the nut plus 100 mm. This is the body height. Okay, and then maximum height of the nut. Okay, anyway, this is the thing. Okay, now let us come to the design. Okay, the designing of the screw, the first step. What is the first step? You see, now there is a heavy load W acting on the cup. Okay, so therefore a direct compressive stress is induced in the screw due to application of this W. Okay, you see here, this W is so heavy. you know Now what happens, the threads that are inside here, see, the load is coming on the cup is sitting on the head. Okay, head is putting the load on the screw, and this screw's load is being transferred to the nut here. So the screws, the threads in the screw and threads in the nut, they are meshing. They are sitting one upon the other. So they will be experiencing crushing there, compression there. Okay. So when they are experiencing compression, okay, there is a compressive load induced in the screw. Okay, and what is the resisting area for that compression? That is the least area. See, now we have three diameters. One is DO, which is the outside diameter, nominal diameter. Second is DM, which is the mean diameter, and third is DC, which is the core diameter. Which one we should take? Which of the three is small? The small will give you the smallest area. So it is DC, which is the smallest. We have to take DC here in this formula. Okay, so the compressive stress is load upon area. Load is W pi by 4 DC square. From this you will get compressive stress that is induced. Okay, in addition to the compressive stress in the screw, now compressive stress, where you see this portion is simply hanging, there won't be compressive stress here, and this much portion inside this nut is sitting inside. Okay, it is like in a nice grounding it is having, right, support it is having. But this portion of the screw that is there, and this is the thing which may get crushed because of that crushing stress. Okay, so this is the portion where that compressive stress comes. Okay, that compressive stress. Apart from that, in addition means apart from that compressive stress, screw is also subject to torsional and shear stresses. You see, now we are with the Tommy bar, we are rotating that head. Okay, when we are rotating, what, some torsion comes, so shear stress is induced because of that torsion. Okay, for this, increase the value of the core diameter B referring to standard table for screw threads, and again determine the core diameter. See, now here through this formula you will get the core diameter, but this core diameter that you are getting is only on the basis of compressive stress. But apart from the compressive stress, shear stress also is there, torsional shear stress. Therefore, what they are saying is, this is the procedure for design procedure. What they are saying is, you see, now because torsional stress is there, this area is only sufficient to bear the compressive load, so you have to increase this area. That means you have to increase the diameter, and you have to choose a standard table. in the data books, and from that you have to choose a core diameter which will be able to sustain this shear stress also. Okay, so that means, you see, suppose this is in our problem, we will see how to do it. You see, if you DC, if you got some 20 or something, so then you may have to, take higher value like 30, 35, 40, something like that DC value you have to take, so that it will be able to bear this torsional shear stress also. Okay, and then now, once you found out that DC from that table, or you have increased the DC, this is the final DC. Now, this final DC, from this you can find out with this relation DC is equal to DO minus which, with this you can find out the other dimensions like pitch and DO. But actually, no, if you are having standard tables, all these things will be fixed. From the table you will get everything. Okay, then, okay, now the what is the torsional shear stress induced? Torsional shear stress induced, you have no T is equal to pi by 16 d cube. From that only this formula came. Tau is equal to 16 into T1 upon pi d c cube. Okay, in this formula, what you have to do is torque, okay, this formula you keep it like this. So torque required to rotate the screw, we have that formula, T1 is equal to W into tan 5 plus alpha into dm by 2. Okay, this is the torque required. Okay, so from this you get torque, and you have got DC. So all these values are known. Now you can find out what is the shear stress. Now when you are finding what any shear stress, no, that means what you are finding, the induced shear stress. You find out, and what they are saying, check whether the principal stress is less than the permissible stress. Whether the principal stress. Now principal stress means what? You see, one stress here you got compressive stress. Another stress you have got shear stress. One is sigma stress, another is tau stress. So you have to find out the principal stresses. Now to principal stresses we have two formulae. One is the maximum principal stress formula, another is maximum shear stress formula. This is the maximum shear stress formula. You insert these two values, this value and this value here, okay, in this, and you find out, and this you have to check whether this is less than the permissible shear stress for that material. And then again you check for the maximum principal stress by substituting these two values of sigma c and tau here, and find out what is the maximum principal stress, and compare with this you should compare with the shear stress, you should compare with the tensile or compressive stress, whichever is given. So this is the procedure for designing of the screw. That means screw means what all we have designed. We have found out what is the core diameter, what is the pitch, and what is the nominal diameter, and we have checked whether this is within the permissible limits or not. Okay. Now next thing is design of nut. Now design of nut, the see, now we know DC, and this DC will be same here also, DC, and this DO will be same DO also. Now what is not there in the nut? In the nut, what is not there is the how many threads should be inside this N. You see, the screw is long, but nut has only fewer threads. What are those fewer threads? And this, once we decide this N, what will happen with that? You'll be able to determine how high it should be, because depending upon that N, if you multiply by pitch, you will get the height. Okay, let us read here. The threads of the nut and screw are engaged to each other, and there is relative motion between them under compressive load. Hence, nut may fail for bearing pressure. In bearing pressure, it fails. Okay, considering bearing failure, now we have to design this, because relative motion is there. Okay, if bearing is not there, if the relative motion is not there, then we should have designed this for crushing. But now we are designing for bearing pressure. So bearing pressure is load upon area. Now what is the load? Now the load is the area. What is the area? What is the area? You see, it is like concentric circle. Okay, pi by 4 dO square minus dC square. This is the area. It is like, that what is it called, like a donut in the circle, in the hole in the middle. Okay, and in inside diameter and outside diameter having. So this is the area. And how many such threads, such areas will be there for crushing? N number. So this into N will be the total area. So load upon area will give you the bearing pressure. This bearing pressure should be given in the problem. Okay, from this you can find out what is N. Okay, so the number of threads engaged with the nut is determined by the above equation. The height of the nut can be calculated as, you see, height of the nut means what are we talking about? This height of the nut. You see, from here to here, this H is written here, no, that one. How much is the height of the nut? Height of the nut is N into pitch. Okay, and once you do that, what you have to do is a you are designing on the basis of bearing pressure. Okay, actually, if the load is more, you are increasing, what can happen is all the threads in the nut may fail and shear off at their root. Okay, ये चूड़ी जैसे वो निकल के आ सकते हैं अगर लोड बहुत ज्यादा हो गया तो। मगर क्या, बट अपन शुरुआत में शेयर स्ट्रेस ही चेक से फाइंड कर सकते थे, मगर क्या, इन प्रैक्टिस दे फाउंड आउट दैट it is better to design on the basis of bearing pressure, because on the basis of shearing stress, if you design and find out the height, and then afterwards when you check bearing pressure, it fails. So rather it is better to check, better to design with the bearing pressure and then afterwards check for shearing. Okay, that's what they are doing now, checking for transverse shear in screw and nut. Okay, in screw and nut, whether they are less than the permissible shear stress for the for the nut and the screw or not. Okay, now this is the formula. Now you see, you think where this nut will fail. This is the screw, no? Screw. Okay, screw. Are we having any? See, let me see. I can show you any. Yeah. Initially we just started with. You see, this threads should fail means what? यहाँ और यहाँ ये पूरे सर्कल में कट के ये पूरा थ्रेड गिनना निकल जाना चाहिए। और कितने थ्रेड्स कटना चाहिए? जितने नट के अंदर है वो सब, नट और स्क्रू के बीच में जो मेशिंग होते हैं उतने सारे, ये सारे कट जाना चाहिए। ओके, और यहाँ पर कटने के बाद जो है ना, अभी स्क्रू जो है ना, वो स्क्रू के जगह केवल एक एक सिलेंड्रिकल रॉड बच जाएगा, क्योंकि ऊपर के पूरे चूड़िया निकल गए। ओके, ऐसा शेयर हो गया। ओके, दैट इज द थिंग। नाउ व्हाट विल बी द एरिया? इसी अगर एक थ्रेड पकड़ेंगे, मतलब यहाँ से यहाँ तक अगर थ्रेड पकड़ेंगे, ये पूरा जो है ना एक सर्कल में कटेगा, ये पाई डी हो जाएगा। हाँ, पाई डी बोले तो पाई कोर डायमीटर, पाई डीसी हो जाएगा। ओके, एंड कितना थिकनेस में कटेगा? इतना, है ना, लाइक दैट। सी, लेट अस कम बैक टू आवर डिजाइन। या, yes, here. Okay, now this will be pi dc, and you know uh, uh, this is the thickness of the this thing, nut, thickness of the what is it, thread, and number, how many are there, like that. So pi dc into t into n. Okay, this will be the area. Okay, from this you can find out the shear stress. And similarly, see, screw fail होता है उसका डीसी के पास। मगर नट कहाँ फेल होता है? नट इनर डायमीटर पे फेल नहीं होता, आउटर डायमीटर पे फेल होता है। नट के अंदर, नट ना इनर डायमीटर के पास फेल होने के लिए उसके पास कुछ नहीं है। वो कहाँ पर चिपका हुआ है पूरे नट के साथ? वो आउटर डायमीटर के पास। सो आउटर डायमीटर, ये दो फर्क है। देखो, स्क्रू में डीसी लेना पड़ता है और नट में डीओ लेना पड़ता है। ये दे लो, दोनों लेने के बाद उसके बाद ओके, नाउ ये दोनों को चेक करने का, ये दोनों विद इन द परमिसिबल लिमिट्स है कि नहीं चेक कर लेने का। चेक करने के बाद अगर परमिसिबल लिमिट के अंदर है तो डिजाइन सेफ है। उसके बाद और क्या है? इनर डायमीटर D1 फेल्स अंडर टेंसाइल स्ट्रेस। अभी टेंसाइल स्ट्रेस में कैसे फेल होता है? देखो, अब देखो ये D1 ये है। अब देखो ये लोड ऐसा नीचे एक्ट कर रहा है। ओके, ये लोड ऐसे नीचे एक्ट कर रहा है, तो ये पूरा यहाँ पर एक ये जो है ना, ये पूरा इसको अगर अपन ऐसा खींच रहे हैं, लोड ऐसा नीचे एक्ट कर रहा है, ओके, ये ऐसा खींच रहे हैं, तो ये पूरा यहाँ पर कट सकता है। कौन सा? ये नट कट सकता है, टेंशन में कट सकता है। टेंशन में कट रहा बोले तो क्या है? ये कैसा है? ये सर्कुलर है, π/4 D1 स्क्वायर, और अंदर जो है ना होल है। ये होल जो है ना, वो कौन सा लेना पड़ेगा? वो आउटर डायमीटर लेना पड़ेगा, क्योंकि वो मिनिमम क्रॉस सेक्शन बनता है। तुम थोड़ा ड्रॉ करके देखो, थोड़ा सा इमेजिनेशन की जरूरत है। π/4 D1 स्क्वायर माने DO स्क्वायर, ये कर दिया, और यहाँ से तुमको टेंसाइल स्ट्रेस मिल जाएगा उसके अंदर। और और D2 कैसे फेल होता है? D2 जाना, ये जो फेल होता है, ये D2 कौन सा? ये D2। अब देखो ये जो ना, ये इसके ऊपर बैठा, ये यहाँ पर सीट जैसे बैठा ना, तो ये क्रश होता है, ये क्रशिंग में फेल हो सकता है। सो D2 को वैसा डिजाइन करना पड़ता है, क्रशिंग फेलियर कंसिडर करके इसको डिजाइन करना पड़ता है। तो ये क्रशिंग कहाँ पर होता है? देखो ये D2 है और ये D1 है, ये D1 है, ये दोनों के बीच में जितना गैप है इसी में क्रश होगा, और इस साइड मतलब पूरे सर्कल में हो जाएगा। ओके, सो वो क्रशिंग का फार्मूला क्या है? π/4 D2 स्क्वायर माइनस D1 स्क्वायर। इससे क्रशिंग पता चल जाएगा। ओके, ये इससे तुमको D1 मिल जाएगा, इससे तुमको D2 मिल जाएगा। उसके बाद थिकनेस ऑफ द कॉलर। तुमको ये प्रश्न आया होगा यहाँ पर, ये T कहाँ से मिलता है? दिस इज T इज नथिंग बट P/2 पिच/2 थिकनेस है ना, अपन स्क्वायर थ्रेड्स की बात कर रहे हैं ना, वैसा है। ओके, नाउ थिकनेस ऑफ द नट कॉलर T1 फेल्स अंडर shear स्ट्रेस। अब देखो ये जो T1 है, ये T1, ये जो है ना, अभी ये लोड ज्यादा हो गया तो ये यहाँ पर ऐसा कट जाएगा, यहाँ कटेगा और यहाँ कटेगा। ये shear स्ट्रेस कंसिडर करके उसको डिजाइन करना पड़ता है। तो ये कैसे कट रहा है? ये पूरा कट रहा ना, यहाँ कट रहा, यहाँ कट रहा, बोले तो पूरा सर्कल में कट रहा, मतलब πD1 में πD1, और कितना थिकनेस में कट रहा? T1 में कट रहा। सो πD1 T1 विल बी द एरिया. So πD1 into T1 is the area. So tau is equal to W upon this, and from this you can find out T1. So यहाँ से D1 मिल गया, यहाँ से D2 मिल गया, यहाँ से T1 मिल गया। उसके बाद you have to design the lever. This lever design, see, this is not in our syllabus. अपना सिलेबस में इतना ही है, क्या है? स्क्रू को डिजाइन करो और नट को डिजाइन करो। और तुम बोलोगे कि ये सारे प्रोपोर्शंस का क्या करें सर? ये सारे प्रोपोर्शंस के बारे में आपने को कुछ नहीं करना है, ये तुम्हारे सिलेबस में मतलब एग्जाम में नहीं पूछा जाएगा। अगर तुम इसका अगर चार्ट वगैरह बना रहे हो तो यहाँ तो सभी चीजें एम्पिरिकल रिलेशंस ही है, तो डायरेक्टली एम्पिरिकल रिलेशंस में वैल्यूज डालो, तुमको मिल जाएगा। और वैसे तुम क्या कर सकते हो? इसका ड्राइंग वगैरह बना सकते हो, ठीक है। मगर अपने को ज्यादा इंटरेस्ट किस में है? इसके अंदर ही इंटरेस्ट है, नट और स्क्रू और नट के बीच में, उतना ही इंटरेस्ट है, बस उतना ही डिजाइन है, ठीक है। स्क्रू जैक का डिजाइन खत्म हो गया, उसके बाद अपन टॉगल जैक देख सकेंगे, बाद में देख लेंगे, और प्रॉब्लम्स भी कर सकते हैं। ओके, तो आज के लिए अपन यहाँ पर रुक जाते हैं। थैंक यू वेरी मच।